Okay, welcome everyone to Math 95. Summer 2025, and today is the 23rd. We're going to cover a couple sections from chapter 1. Our first section that we're going to cover is section 1.1, which is called qualitative graphs. But before we do that, I want to introduce you to a visual I like to use that I really encourage you to adopt as a way to think about all the math in this class and all the math in any class you do, and basically any math that you do at all. And I call this the 4 representations of mathematical ideas. So probably all of you at some point have seen math represented as functions and equations and symbols. So I call that the symbols representation of mathematical ideas, something like x squared plus 1. And I put this at the top of our representation because often in math it's kind of presented as the most important. I don't actually think it's the most important, but you'll probably see it presented that way. A lot of the math we do is represented with symbols. However, being human beings, we tend to think verbally, right? We think in words or verbal representations. And so one of the skills in learning math is to be able to go back and forth from a symbolic representation to a words or a verbal representation. And often this is what's focused on, especially in the math leading up through Math 95, and we don't think about the other 2 representations as being equally important. But human beings are not only verbal, we are also very much visual learners. And so there's a visual representation, which is often graphs, but not always graphs. And so we're going to spend a lot of time in this class working on how to go from words to visual or from symbols to visual and vice versa. And then the last representation that's often kind of discounted by math teachers is the idea of numbers. If you ever heard of guess and check, plug and chug, sometimes it's like, well, yeah, you can do that, but that's not really the math. You're not doing the math until you can do it with symbols. But I don't actually believe that. I think using numbers to understand mathematical ideas is really powerful. So going between numbers and words, numbers to visual, and often numbers, when talking about mathematical ideas, are presented as tables, but not always. And then going from numbers to symbols. So there will be a question probably on your final exam if you can write down these 4 representations. And even better yet, use them to represent a mathematical idea. So I'll be coming back to this. I'll try to highlight when we study new mathematical ideas, each of the 4 representations. Some mathematical ideas do better with only 3 of these, right? Others do fine with all 4. So let's use this idea to study our first section, qualitative graphs. And really, this whole idea is going between words and visuals in math. So let's just do an example. Jane runs at a constant speed for 10 minutes. Draw a graph that represents how far Jane travels over the 10 minutes. So this is a classic verbal representation of a mathematical idea. If Jane runs at a constant speed for 10 minutes, we could figure out how far Jane has run over the course of those 10 minutes or at any point in those 10 minutes. And we're going to convert this verbal idea into a visual idea. If this is time on our horizontal axis and total distance on our vertical axis, well, at the very beginning, how far has Jane run? 0. So 0, 0, right? That point right there is probably going to be on our graph. And now we have to decide, what is this graph? What is the line going to look like as time increases? Well, if she's running at a constant speed, each minute that goes by, she adds the same amount of distance. And so she's going to end up running in a way that makes her total distance accumulate in a straight line. That's the basic idea for these qualitative graphs. Can you go from a verbal description and put it in a visual description? And that gives us the ability to maybe answer some questions that would be more difficult to answer using a verbal representation. Anybody have questions? Okay, let's do one that's a little more challenging. Roberta goes for a run. She starts slow for 5 minutes for the warm-up. Then runs at an increasing speed for 5 minutes. Then holds the maximum speed for 5 minutes. And then stops and stretches for 5 minutes. And we want to represent this with a graph. So we're going to graph total distance traveled. Notice I'm not putting many numbers on here at the moment, because really, again, we're just trying to get the idea of how a graph can represent a verbal description. However, there's a lot of, I mean, if you're going to approach this and you're like, well, there's a lot of stuff going on here, and I'm not really sure how to do each segment. You could, before going to a graphical, you could do a numerical representation. You could make a table, for example. And this is what I want you to kind of think about is like, is there a time when I want to go from words to visual, where it might actually be easier to go from words to numbers and then from numbers to visual, right? To use those relationships. So let's use a table, and we have time here and distance here. And let's count. We might not always want to do this amount of detail, but we could do all 20 minutes. I know you can't see that last little bit, but that's okay. There we go. Okay. So the first 5 minutes, Roberta is running in a slow pace. I should probably put a 0 on there too, shouldn't I? 0, 1, sneak a little 0 in there. Because at 0, Roberta's gone 0. And she's running kind of slowly. So let's say as time goes by, as the minutes go by, she adds, oops, right, maybe only not a mile, but five laps. I don't know, let's call it 5 laps every minute. But now she's going to start running faster. So the next minute, she's actually going to increase. Instead of going 1, maybe she's going to go 2. And then instead of going 2, she's actually going to go 3. And then instead of adding 3, she's actually going to add 4. And then she's actually going to add 5. And then she's actually going to add 6. And now she's going to hold that maximum speed for 5 minutes. So she's adding 6 laps every minute. All right, so she's going to go 31 and 37 and 43 and 49 and 55. And then she stops and stretches for 5 minutes. So what's going to happen in the last 5 minutes? Is she going to add any distance? Nope. So she's just going to stick at 55. Now that's an awful lot of detail for our graph, especially a hand-drawn graph. So let's switch over and let's look at Desmos. And for those of you watching online, you're not going to be able to see this, or maybe I can switch. I'll switch the screen. Okay, so this is Desmos. This is a graphing calculator that was first developed about 15 years ago, and it's been improving ever since. And it's a pretty amazing tool. You can do basic calculations pretty easy. 13 times 10, it tells you right there, 130. You can graph super easily, x plus 1, and it just puts a graph right on there. You can use that graph and find where you are on that graph pretty easily. You can even, and we'll get into this a little bit later, if you haven't seen this notation before, this is a symbolic representation. And once I define my function as to say the input plus 1, now I can see what the output is when the input is 4. And these are just a few of the capabilities. And the one we're going to use is the ability to do a table. And so we're going to put our time in the X column. And we're going to put our distance traveled, total distance traveled in the Y column. Another thing to keep in mind is I'm zooming in and out just with the roller wheel, but you can also change a little more directly. There you go. Your field of view. And now we have a pretty nice picture of what's happening in our function, in our description. Now, these are only points, but we can connect these points pretty easily. That looks like it's straight. This looks like it's actually curving up because Roberta's accelerating. This one's straight again, and then this one's flat. So now I can take that and I can bring this over. Okay. Oh, wrong one. Desmos. There it is. Now I can bring that over and I can plot on my graph pretty easily. So it starts straight and then it curves up and then it goes straight, pretty steep up, and then it goes across. A lot of times when you want to go from a verbal to a graphical, you're going to be fortunate to have more details in the verbal, right? It might actually give you more information about what those coordinate points are going to look like. But I just kind of came up with this example off the top of my head. So I didn't have a lot of real strong details. And we just filled in some of our numbers to give us a general idea. Straight, curving up, straight, and flat. All right, one more example. And this is different mathematical ideas from the same description. So Carl walks from home to school in 10 minutes. He sits at school for 5 minutes, then runs home in 7 minutes. We're going to represent 3 different mathematical ideas in graphs from the same description. We're going to represent the total distance traveled. We're going to represent the distance from home. And we're going to represent speed. And part of what you need to do when you're extracting mathematical information, whether it's from a graph, a table, formula, or words, is you need to decide what mathematical information am I extracting. So let's do the total distance traveled, total distance and time. We'll do that first because that's what we've already done. Okay, so Carl walks from home to school in 10 minutes. So he gets maybe that far. And then he sits at school for 5 minutes. So is Carl accumulating any distance? Nope. So he's going to stay at that level of accumulation for 5 minutes. And then he runs home in 7 minutes. So now he's accumulating more distance, a little bit faster. So in a little bit less time. If Carl had a pedometer, that pedometer would always be going up. All right, no matter where Carl's walking, you don't get negative steps on a pedometer or a Fitbit. Going to get into this century. Well, let's consider now distance from home over the same amount of time. Well, at the beginning, as Carl's walking from home to school, he's getting farther from home. So it's going to look the exact same. And then the whole time Carl's at school, is his distance from home changing? No, so it's going to stay the same. But what about when Carl runs home? What's going to happen to his distance? It's actually going to go down. Slightly different graphs because they're representing different mathematical ideas. Now let's think about Carl's speed. Carl walks to school. Let's assume Carl walks at a constant pace. So speed is actually going to be a constant speed for the amount of time that he's walking to school. How fast is Carl walking at the beginning? 2 miles an hour. How fast is Carl walking when he's halfway to school? Still 2 miles per hour. What happens when Carl gets to school? What's his speed? 0. So now his speed is going to drop down here and be 0 the whole time he's sitting at school. And then Carl runs home. And it doesn't take him as long, so he must be going faster. So for the time he's running home, his speed must be greater. And I didn't even do velocity, which would say, well, if he's running home, his actual velocity would be negative because he's moving in the opposite direction. I just said speed, right? We could pull out even more mathematical ideas from this one simple sentence, maybe 2 sentences. So in my mind, the 2 biggest challenges in this section with these qualitative graphs is, one, understanding the difference between traveling at a constant speed or maybe at an increasing speed or maybe not moving at all, and how those look different. And 2, trying to decide what's the mathematical idea that I'm actually trying to graph or that I've been asked to graph. As you work on your worksheet, sometimes you may graph one that, like the quote unquote wrong one, even if your graph is mathematically correct, it's not showing the idea that I'm looking for. Okay, let's take a break. Let me pause this video. Let's pause sharing. All right, one more idea from our qualitative graphs. And then we'll switch to section 1.2. But before that, I'll have Gabe introduce himself. So key elements that are easy to identify from graphs. All right, one reason that visual representations are useful is there's some elements of mathematical ideas that are pretty important that graphs make it pretty easy to see. And those ideas are intercepts and increasing, decreasing behavior. So within the intercept idea, we have the y-intercept, which has at most each graph of a function will have at most one y-intercept. And we have x-intercepts, and you can have possibly many. Well, the most generic way to show a graph is to do a coordinate axes where they can cross. We usually label the horizontal axis x and the vertical axis y. And I'm going to draw a visual representation of a mathematical idea. It's not really related to anything, but it looks like that. And hopefully you can see that it crosses your coordinate axes in 3 places. It crosses the y-axis. At the y-intercept. And it crosses the x-axis in 2 places. And so we have 2 x-intercepts. And if I put a scale on here, the y-intercept, it has an x-coordinate is 0, because when you're vertically above the origin, your x-coordinate is 0. And the y-coordinate is 2. And so we would write that as x comma y equals 0 comma 2. The x-coordinate of the y-intercept will always be 0. And our x-intercepts are -4 comma 0 and 3 comma 0. Your x-intercepts will always have the y value equal to 0. We're going to come back to this a lot. I just want to introduce that idea to you. Identifying x and y intercepts. Okay. Let me redraw the same graph. Go. There's our 2 x-intercepts and our 1 y-intercept. And our graph is increasing when, as you move from left to right, your graph goes up. And it's decreasing when, as you move from left to right, your graph goes down. So we have another section where it's increasing. And then another section where it's decreasing. Now, in my experience, the graphical representation is the easiest way to tell what your intercepts are and where your function or your graph is increasing or decreasing. It's not too hard in the numerical one either, right? If I had a numerical representation of this, it would look something like something like that. Right, and I just pulled all these numbers from looking at my graph right here. And I can see, aha, there's an x-intercept. I got two of them actually. And there's a y-intercept because the x value is 0. And as I increase from left to right, this is where it gets a little harder to see. Okay, it's increasing here, and then it's decreasing, and it's increasing, right? It's possible, but it's harder. I think increase and decrease in behavior is by far easiest with a graph. Okay. All right. That concludes section 1.1. I'll jump into section 1.2 in just a little bit, but first let's allow Gabe to introduce himself. So I'm going to pause. All right. Section 1.2. Functions. So a function, first of all, is one of these mathematical ideas. Which means it can be represented usually in the four different ways. There are functions that do not lend themselves to representation in one of those four ways, but most of the functions we'll study here can be. At its core, a function is a set of instructions that are clear and consistent. And pair an input with an output. So that's a definition that's probably useful to carry around with you. This clear and consistent piece, I think, is very important because ultimately functions allow us to do things, but you can't do something if you don't know what to do, right? If it's not clear, and you can't do something consistently if the instructions aren't consistent. Inputs are often labeled X. Outputs are often labeled Y. Let me give you an example of a function. We're going to take the name of the student as an input and pair it with their breakfast this morning. I won't ask you all because maybe you didn't all have breakfast, but that's fine. Jane had oatmeal. Roberta had coffee. Carl had oatmeal also. And Jim had nothing. So if I asked you what did Roberta have for breakfast, you could tell me coffee. Is that pretty clear? Yeah, because there's that nice set of instructions right there, right? This is a pairing. If I said, wait a minute, what did Roberta have for breakfast? Coffee. Is that consistent? Every time I ask you what Roberta had for breakfast this morning, you give me the same answer. Okay. What did Jane have? Cool. So I definitely know what Jane had. What did Carl have? Oatmeal. So I definitely know what Carl had. Very clear, very consistent. Jim had nothing. That's okay, right? Sometimes you get an input that pairs with no outputs. That's okay too. All right. Here's example of maybe a function that we're more used to seeing. And I'm going to do this in a table form. So we're going to have a set of inputs, 0, 1, 2, 3, and 4. And we're going to have a set of outputs, 9, 6, 3, 0, and -3. If I say the input is 2, can you tell me what the output is? 3. Every time? Yep. In this case, yes. All right, so these are clear and they're consistent. This function represented numerically could actually be represented in a symbolic form as well, where you could say the output is going to be 9 minus 3 times whatever the input is, 9 minus 3x. So we have a numerical representation and we have a symbolic representation that give us the same information, at least on the x's that we know. If I put x equals 2 into this formula, I'd have 9 minus 3 times 2, which is 9 minus 6, which is 3. I could put this in a graph. Let's see. 1, 2, 3, 4. 2, 3, 4, 6, 3. X, Y. There. 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 Technically, this is all I know. Based on my table, if x is 2, what is y? 3. Based on my table, if x is 2.5, what is y? We don't know. All right. This function only tells me about the numbers 0, 1, 2, 3, and 4. So in my visual representations, I only have the numbers 0, 1, 2, 3, and 4 for my x values. Often our numerical representation only gives us part of the information. Or we could do that logical leap and say, well, probably if I chose other x values, I could figure out what they are. But our table doesn't give us that information. Okay. And I'm going to give you an example of a set of pairs of inputs and outputs where the instructions are not consistent. So we'll do it with the table again, x and y. And I'm still going to take 0, 1, 2, 3, and 4 because that's easy for me. Let's see. Y is the y's are -2, +2, 0, 1, 3. And I'm going to come in here and I'm going to give it a 2 again. And this time I'm going to send 2 to 5. Well, what output is paired with x equal 2? Sometimes it's 0 and sometimes it's 5. But the pairing is not consistent. So these instructions are not, quote unquote, easy to follow. Nothing wrong with these pairings, but I couldn't use them as a set of instructions because I wouldn't know to send 2 to 0 or send 2 to 5. And that would be a problem. So this pairing, right, these sets of pairs does not come from a function. From X to Y. Okay. All right. Circle the issue. Sometimes 2 gets paired with 0, sometimes 2 gets paired with 5. So we don't have clear and consistent instructions on what to pair with the number 2. Let's talk a little bit more about inputs and outputs. The set of inputs in the function is called the domain. Just a piece of vocabulary that you're going to need to keep track of. You're going to hear something or read something like, what's the domain of this function? Let's go back to that function I used that my x's are 0, 1, 2, 3, and 4, and my y's are 9, 6, 3, 0, and -3. The set of outputs is called the range. So in this function, represented by a table, the domain are the numbers. X is in the set 0, 1, 2, 3, and 4. And the range, Y is in the set. Often you'll see arranged smallest to largest, like in numerical order, but I don't really care. As long as they're all in there, that works. It's the set of outputs, 9, 6, 3, 0, and -3. Numerical representations are by far the easiest for identifying the domain, because you just get a list of numbers that you see in the X column. And for the range, you list the numbers that you see in the Y column. You don't have to repeat it. If I had 6 show up a bunch of times in the Y column, I only have to write it once. Graphically, a little more challenging. Let's look at a function represented graphically. So here's my X and my Y. Let's do a version of that M function that I had earlier. Where this point here was 3. This point here was -4, 0, so 0, 3 here. The height, sorry, the height of that is 3. Yeah, this point is 0, 2. And this point was 3, 0. So for identifying the domain in a graphical representation, what I like to do is I like to imagine shining a flashlight vertically and seeing where the shadow lands on the x-axis. So if I shine this flashlight vertically, I'm going to have a shadow that stretches from here to here. Those are the x values where the function lives. So the domain would be x is from -4 up to 3. And for the range, I imagine shining a flashlight from the side, maybe from both sides, right, to get the total. And then I say, okay, if I shine the flashlight from the side, where am I casting a shadow on the y-axis? So here the range y is from, well, the smallest number that gives me a shadow in terms of the y is actually 0 up to 3. The functions can be a little more complicated, but ultimately, if you use that shadow method, you should be able to say, okay, where's the function living on the x-axis and where is it living on the y-axis? Symbolic representations, much harder to figure out. We will, but I'm not going to show you now. And verbal representations can sometimes be super easy or sometimes be hard. All right, last piece of information. Speaking about domain and range, and the way I wrote this, I said domain x is from -4 up to 3, and y is from 0 up to 3. I like that, but as you move on in math, you need to learn some of the vocabulary and the grammar for mathematics. So representing things like domain and range, we often use something, mathematics, called interval notation. And just like with our other mathematical ideas, there's numerical, graphical, visual, and symbolic here as well. So let's consider that domain is x from -4 up to 3, including those endpoints. If we look back at our picture, -4 is fine. I actually have a point right there, and 3 is also fine. So graphical. Oh, sorry, this is verbal right there, right? The domain is x from -4 up to 3. Graphical, well, I'm only talking about x values, so I just need an x number line. I don't need everything. And I like to orient myself by putting a 0 in the middle. And then I'm just going to count down to -4 and up to 3. And if the domain includes these points, I'll shade in all of that, like so. And because I include -4, I want to make that really obvious, so I make my shade a dot at the end. And personally, well, I'll say that in a minute, sorry. And then symbolic. There's actually two ways to represent this interval in symbolic. Interval notation, I find to be the simpler. I look at my interval and I say, what's the smallest important point on here? -4. What's the biggest important point on here? 3. Do I get to include everything between those? It's all shaded. So yes. All right, so I'll just put a comma. Now I look at the dot. Am I allowed to include 4, -4? All right, so to do that, I'll put a square bracket. That's our mathematical grammar. That implies include the -4. Whoever the mathematician was who came up with it, they could have picked any symbol. That's the one they happen to pick. But we're including the 3, so what should we put on the other side of the 3? Square bracket. Now, I think there's one really important thing missing from this interval notation, and that is, what am I actually talking about? So for interval notation, I always like to write X is in the interval, and then I write the interval. Otherwise, this could mean anything, right? It's like back when you were learning about units and like, well, what are the units? Could be goldfish, could be elephants. You have to write your units. This is kind of like that idea. Okay. The other type of symbolic notation, it's called set builder, but I call it inequality notation. And it's the same idea. You say, what's my smallest important point? -4. What's my biggest important point? 3. Everything between them is fine, so I stick X between them. And I see that X needs to be bigger than or equal to -4 or less than or equal to 3. Domain and range are actually really important mathematical ideas because most of the math we use to model real situations, like a pen going up and down, we can model mathematically, or a rocket ship, or many other things that matter more than a pen in a classroom. But the model I use only works for a certain amount of time, right? If I use a basic model for this pen, it breaks as soon as the pen hits the ground. So I need to know what are the time values that make sense in that model. That's exactly what the domain is. Sometimes it seems a little abstract, but that's really where it comes back to matter. Okay. Other types of intervals. We have open intervals. So what if I have X is from -2 up to 7, not including the endpoints. That's my verbal. My graphical, similar. Draw a number line, stick a 0 in the middle. 2, 3, 7, 2. Get my numbers on there, -2 up to 7. So we still get to shade what's between -2 and 7, but to show that we're not including it, we put an open circle around those points, like that. That's our mathematical, our visual grammar to indicate that it is not including those endpoints. Symbolic, we take -2, which is one of the important points. We take 7, which is one of the important points, stick a comma between them. And to show that we're not including them, we use open parentheses, which is a really bad idea, I think, because is that an interval? Is that a coordinate point? Who knows? And so I write x is in the interval -2 to 7. And that's why I think this piece of the sentence is important, because it shows us we're actually talking about an interval. And if we want to do set builder or inequality notation, we use a strict inequality. -2 is less than x is less than 7. Last topic. One more type of interval. These notes will be up here. Which are called unions of intervals. So let's actually look at a graph here. See what that might look like on a graph. Let's put a dot there at -5 and an open circle here at -1, and then jump over here to +2 and do an open circle, and then we'll go out forever and ever and ever. I have no idea what function that graph represents, but I know it's a function because if you tell me an x value, it's always going to give me the same y value. Unless there's no y value. It's like Jim, who didn't have breakfast. Doesn't mean it's not a function, just means Jim is not in the domain of the breakfast function. So if I want the domain of this function, again, I think if you shine that flashlight, it's the easiest way. If you shine it from the top and the bottom, you're going to see, aha, -5 is part of the domain. And I actually like using the bracket notation as opposed to the solid dot because that connects better with me for the symbolic. And then all of this is going to be shaded. And so we get up here to -1, and it's not going to include the -1. I'll put a parentheses there. And then I'm missing some. There's no domain between -1 and 2, but 2 restarts my domain. I can't include 2, so I'll use a parentheses or an open circle. And then I'll keep going on forever and ever and ever. And that actually right there, that is my number line that I was showing you on the previous page. So symbolic would say x is in the interval. Let's see, -5 up to -1. And the -5 is included, so I use that bracket. The -1 is excluded, so I use the parentheses. And, well, I just use the word and. From 2, with the parentheses, because you don't include the 2, up to forever. What's the word for forever in numbers? Yep, up to infinity. Can we ever reach infinity? Nope, so we'll use a parentheses there as well. Infinity always gets parentheses. Now, our mathematical grammar has a special symbol for the word and when we're talking about interval notation, which is called the union symbol. I don't personally care. You can use an and, you can use a comma. Your homework will require you to use the mathematical grammar, and it just looks kind of like a capital U. So that's how we do unions of intervals. collections of intervals.